what I wanted to do next was talk a little bit about trabecular bone, because one of the things about trabecular bone, remember I brought in that, I think I brought in a hip joint thing the first day. So trabecular bone is that porous type of bone. It's sometimes called spongy bone or cancellous bone. It grows in response to loads. So if you load your bone more, it grows denser, and if you load it less, it grows less dense. So there's a couple of places where it's really obvious that this happens. So if you look at professional tennis players and you look at their arms, their bones in their arm of the dominant hand, the one they hold their racket in, gets bigger than the bone in their other arm. And people have done studies where they look at professional tennis players, and it's noticeably larger and denser. The other sort of extreme is astronauts. You know, when astronauts go up into the space station and they're up for several months, they have all these kind of contraptions with springs and treadmills, and they're trying to exercise. And the reason they're trying to exercise is if they don't, they lose bone mass and they can have problems when they come back to Earth. So if they don't get loaded in lower gravity, the bone mass goes down too. So anyway, the bone grows in response to load. And one of the things about the trabecular bone is that the pattern of the bone follows the principal stresses. So that's why I'm telling you about it right now. So that the pattern of the trabecular bone is almost like a manifestation of these principal stresses. So the idea is, with the principal stresses are the maximum stresses, right? So the bone is kind of growing where the stresses are maximum. So it kind of physically that would make sense. So there's sort of an interesting thing that sort of arises connected to that. So let me scoot the screen down again. And I'll put, I think these notes will be up on the MITx website, so I won't, you don't need to write much down here. So people have made use of this fact that trabecular bone grows in response to loads in looking at human evolution, and I thought that was kind of an interesting thing to talk about, so this seemed like the right spot to talk about it. So, whoops, let me see, I've got my little clicker, have to turn it on. Okay, so, here we are. So these are pictures of trabecular bone here. It exists at the ends of your long bone. So this is a femur. This is the ball at the end of your femur that fits into your pelvis. This is a tibia, so this is your knee here. And this is a vertebrae here. Okay, so the trabecular bone is the porous bone, and it's at the ends of the long bones. It's in your vertebrae. It's inside your skull. And the reason it's there really is because, like, if you think of the ends of your long bones, they're at a joint. Your body's trying to distribute the load over a bigger area, but not have a solid bone, have a sort of lighter thing than the solid bone. So that's kind of physically what it's doing there. These are just some other microcomputed tomography images of trabecular bone, so you can kind of see what it looks like. So the idea is that bone grows in response to loads. The architecture reflects these principal stresses, and the bone structure reflects the mechanical loading and function. And anthropologists have used the trabecular architecture of fossils of extinct species to try to figure out if they were bipedal or quadrupedal. So, one of the things in human evolution is, when did we start walking? When did we become bipeds? And, they get all these fossils, and you can't, they're fossils, they're not going to get up and walk. So they want to have some way of trying to figure out, was some species a biped or a quadruped? And one of the ways they can do that is by looking at the bone. So what I'm going to do is talk about something called Wolff's law. So Wolff's law is basically the idea that bone grows in response to loading. People have done some nice experiments with guinea fowl. I like birds. So they run guinea fowl on treadmills. And I know it's rather amusing. They run the guinea fowl on treadmills, and you can show if you incline the treadmill, you can change the orientation of the bone. So we'll see that. Then there was another study done where they looked at the trabecular bone architecture in primates, in living primates. And you can think about, if you think about the way we walk, we're on two legs. If you think about the way a chimp walks, it's kind of on two legs sometimes, but not all the time. If you look at a gorilla, it's kind of more on all fours. And then the other species they looked at is the orangutan, and orangutans brachiate. They swing through the forest with their arms. So they're comparing a bone and looking at the structure of the bone for these different existing primates that move by different means. And then there's another study I wanted to talk a little bit about that looks at an extinct hominid and tries to make the argument that the architecture of the bone shows evidence that this was a bipedal hominid. And I wanted to mention Brian Addison. He's a PhD student in biology at Harvard, and he was the one who kind of put me onto this stuff. So this is Wolff's law. This is Wolff's original drawing. And the story is that Wolff was looking at trabecular bone, and he was, making these kinds of drawings of the pattern of the trabeculae in the bone. And a colleague of his came along and said, "That's my crane." The other guy was looking at the stress trajectories in a crane, and they noticed that the way the stresses were transferred through the crane was similar to the bone. And that made them think, oh, the bone is growing in response to these loads. And this is just a picture of the bone again. And this is just another example of that. This is a cantilever beam. So say you have a beam here and you're loading it up here. This would be the principal stress trajectories here on this side. And this is a bone in a horse, a thoracic vertebrae. And it has this kind of pointy bit that goes off. And this is kind of a sketch of the whole thing if you loaded it like that. And you can see the trabecular orientations here. These little sort of arches kind of correspond to that stress trajectories in the cantilever. So that's kind of Wolff's law. So the idea is that the trabecular orientation matches the principal stresses in a continuum of the same shape and the same loading. But when you think about it, the bone cells in the bone, they don't really see the continuum. And recent studies have shown that the bone remodels in response to a local strain energy per unit volume. So remember we talked about strain energy in the linear elastic stuff? So this is sort of an example of using that. So the idea is that the bone remodels to maintain a constant strain energy per unit volume. And that gives the same orientation as if you were matching the principal stresses in the continuum. So here's a set of experiments on bone growing in response to loads. So here's our guinea fowl. And they took 3 sets of guinea fowls. So one set they ran on a level treadmill. And what they did was they had a force plate under here. And they measured the orientation, the sort of angle here of the femur and the, I guess, tibia when the force was maximum on the force plate. So they measured this angle here. That was one set. They had a second set, and they made the treadmill at a 20-degree incline. And the same thing, they measured that angle. And the thing that they measured was that there's a difference in the angle of the bone at the maximum force. So here it was 76 degrees, here it was 63 roughly. So there's roughly a 14-degree difference between the two. So when the guinea fowl are running on the treadmill, there's about this 14-degree difference. And then they had a third set, a control set that weren't running on any treadmills. And these were juvenile guinea fowl. So the idea is when it's a juvenile, their bones aren't completely sort of set, and that they're more sort of pliable. They're more likely to remodel. It's easier to get them to remodel. So they used the juvenile guinea fowl for that. And then what they did was they sacrificed the guinea fowl, and and then they looked at the orientation of the trabecular bone. And the way they did it was they used X-rays, and they looked at the intensity of the X-rays. So imagine you have, this is sort of a model structure. Imagine you had 3 trabeculae this way, and you're passing the X-rays that way. You would get less transmission of the X-rays than if they were this way on. So depending on what the orientation of the trabeculae is, you get more or less of the X-rays passing through. And they used that to sort of make an estimate of what the orientation of the bone was. And they determined something they called the orientation of peak trabecular density, so OPTD. We're going to see that again. And then they used some kind of very standard images to calibrate the whole thing. So this is what they found. So here's one of the bones, and these lines correspond to this orientation of the bone. And the red is for the guinea fowl that were run on incline, the blue is the level, and the yellow is the control. So you can see the level and the control are not very different, but the ones that were run on the treadmill, on the incline, were different. And they have a little table here, and if you look at the angular difference of the trabeculae between the incline and the level, and the difference in the angle of the joint at the peak ground force, they're almost identical. So that the bone, the humor or the femur and the tibia angle changed, and the bone orientation changed by almost the same amount. And if you compare the level and the control, they didn't change very much at all. So this is trying to demonstrate that the bone is growing in response to loads that are on it. Okay, so the next little study was on existing primates, and they looked at the calcaneus. The calcaneus is your heel bone. It's kind of the bone right under there. And they looked at these 4 primates, and they used something called a star volume distribution. What you do is you put an array of points down over some structure, and then you measure the distance and the orientation of lines drawn from those points. And This diagram here kind of shows what they did. So here's for a human, this is a sort of a X-ray picture of the bone, and you can see the bone is very oriented, and even your eye can kind of pick it up on that X-ray. It's more oriented this way and that way, so there's sort of preferential directions. And that's because we're walking on our heels. You know, we're doing this, and the bones tend to lining up that way and that way because we're walking on our heels. I think the chimp is the next sort of most similar to us, spends more time on 2 legs, but some on 4. And you can see it's a little less oriented in the structure. And then the gorilla is even less. It's sort of more, you know, this direction here is more similar to that one there. And when you look at the structure, it's harder to pick out sort of preferred orientation. And then this is the orangutan here. And you can see that structure is almost random. It's not really oriented at all. And that's because the orangutan it's not really on its heels a whole lot. It's, you know, swinging through the branches with its arms. So the heel bone doesn't really orient very much at all. So that's kind of just showing, again, the bone orientation relative to the loading. Oh, and here's some numbers. So this is the degree of anisotropy. Remember, we've talked about anisotropy with Young's modulus. This is more just anisotropy of the structure. And the human is the most anisotropic. We're the most oriented because we load our bones, our heel bone up and down when we walk on it. And then this is just the volume fraction of the bone. It's sort of, obviously way less than a gorilla, so not too surprisingly our bone is less dense than the gorilla. And then this is the sort of the most interesting thing, I think. This is looking at an extinct hominid, something called Oreopithecus bambolii. And they were trying to figure out if this is a biped or a quadruped. And they found fragments of the ilium. So just to remind yourselves, the ilium is part of your pelvis. So that's just kind of a drawing of the pelvis. And when people look at bone in different species, there's certain anatomical landmarks. So they can look at a bone in one species and another, and there's locations that they can compare. And this is just showing two bones, one from a human and one from a siamang, which is another primate, and these comparative positions. And this is the fossils that they found. And they found 2 fossils, and they made up the whole bone from these 2 pieces, and they did a little digital reconstruction. And all these little labels are these anatomical landmark positions. And then what they did was they compared the fossil bone, so these pictures here from the fossil bone, and these are the same equivalent places on a human and on a chimpanzee, on a siamang, and on a baboon. And then they looked at comparing, are they similar or are they different? And if you look at the human bone, there's this dense bit here, and there's a similar dense bit up there. And whereas if you look at the other primates, that dense bit doesn't exist. And you can't really see it on this magnification here, but they were looking at the orientation of the bone here, and they said it was similar to the human, but not so much to these 3 here. Again, there's a little dense bit here on the fossil bone. There's a dense bit on the human. Not really so dense there. There's a tiny little bit there. And the same kind of thing here. These 2 areas are similar. So they were looking at sort of the density and the orientation of the bone and comparing the fossil bone with the human bone with other primates. And by comparing, you know, species that are bipedal and species that aren't, they could say something about the extinct species. So I think that's it for that.